Another trend or factor of ions and elements and that sort of thing that you need to be aware of is that of ionization energy. Now, what ionization energy is, it's the energy that's required to remove an electron from a species, whether it be an atom or an ion in the gaseous state. Remember, we use the term joules for energy. Down here, you'll see the units for these ionization energies are in kilojoules per mole. And there are multiple ionization energies for elements. If you're only going to remove one electron from a particular element, one from an atom of an element, it's called the first ionization energy, or I1, I sub 1. If you want to remove two, it becomes I sub 2 and I sub 3. And this table is found in your textbook, but I want to point out one thing about this table that's kind of important, and you need to realize the cohesion and the reason for one of these big trends in this table. So notice that for sodium element, the first ionization energy is about 496 kilojoules per mole. When it moves, when we start trying to pull off, so that's to remove the first electron from a sodium atom. If you have a sodium plus 1 ion, to remove another electron to become sodium plus 2, the energy required to do that increases by almost tenfold. Okay, so it's almost 10 times as hard to remove that second electron as it is to remove the first electron. For magnesium, the first one is 738, the second one is 1451, so it's about twice as hard, and then the third one is 7,733 kilojoules per mole. So what's the reason for this? Well, the reason is actually that these electrons, this ionization stage, actually is removing or trying to remove electrons from the inner shells. So going back to the periodic table, sodium is right here. Its electron configuration is neon, right? Neon 3s1. So there's only one electron or one valence electron available to remove. So if you remove that one, it's removed from the outermost shell. But when you start removing or trying to remove the second electron there, it has to be from the row 2, so from the principal quantum number 2 electrons in that sodium element or ion. So that sodium ion has to be, or electron has to be removed from row 2. That's considered a core electron. It is vastly more difficult to remove core electrons from a species than to remove electrons in the outermost shell. And that's why you see this kind of stair-stepping as you're moving across a periodic table, moving from left to right along a row across the periodic table. The other thing to point out here is that as you're moving down this column, so this is from left to right across the periodic table, the sodium, to remove an electron from sodium, is 496. From magnesium, it's 738. Why is it increasing down this way? At least for the most part. There's a weird thing with aluminum versus magnesium. It drops down, but it's increasing. The trend is to increase this way. Well, as you're moving down or across the periodic table, your Z effective is getting greater and greater. So that proton is pulling those electrons in closer and closer, and the closer they are to that proton, the more there are more protons at the nucleus. Excuse me. There are more protons at the nucleus as you're moving down this trend, and Z effective is increasing, and so the higher the Z effective, the higher the ionization energy will be. Convention for actually writing these ionizations is shown right here, where if you take magnesium in the gas state, so this is elemental magnesium, and then all of a sudden you remove an electron from it. So this is for the first ionization energy. This is the way to actually write this. So for the second ionization energy for magnesium, you take magnesium ion, so Mg plus 1. You're removing another electron, or an electron from magnesium plus 1, so it becomes magnesium plus 2 plus 1 electron. So this is the way to write first ionization and the second ionization for any, and you would continue on this trend for any element species. So the trends for the ionization energy is, ionization energy increases as you go from the bottom of the periodic table to the top. So it's harder to ionize, or more difficult to ionize elements that are in the higher rows. As you get more and more rows down, you have basically larger and larger electron clouds, so bigger and bigger shells, and basically the bigger the shell is, the easier it is to break, okay? So, and as you're moving across the periodic table, the trend is that you get increasing ionization energy, and again, that's because Z effective increases from left to right. There is one thing to note on this trend, though, is that you'll notice that it doesn't always follow this trend. You'll notice that the ionization energy is actually greater for nitrogen than it is for oxygen, even though Z effective is greater for oxygen. And why is that? Well, the reason is can be seen if you draw the orbital diagram for both of these. So the outermost shell, subshell, is actually the 2p subshell, right? So these are parts of the orbital diagram, just showing the 2p subshell, the 2p subshell. It has 3 electrons right here for oxygen, right? So oxygen, going back there, has 1, 2, 3, 4 electrons. I'm sorry, 4 electrons for oxygen. Yeah, I can count them now. And only 3 for nitrogen. 1, 2, 3 electrons here. Well, if you remove an electron from oxygen, you are essentially moving from a slightly more than half-filled subshell to a half-filled subshell. Whenever you move to a half-filled or fully filled shell, there's a decrease in energy that occurs, and that decrease means that it's more likely to happen. Whenever you break a fully filled shell or break a half-filled subshell, you need to put in a lot more energy to get that to go. And so this is why it is the ionization energy is greater for nitrogen than it is for oxygen, even though oxygen has a greater effective nuclear charge.